This is apparently Felix Baumgartner. I guess it's somewhere in the southern U.S., I would imagine, just from looking at it. And of course, sponsored by Red Bull. What else wouldn't be these days, I guess, for something extreme? And well, all kinds of fluid mechanics. I guess the helium balloon that expands as it goes up because of the pressure change. We know that you can't provide any real constraint on that, and we know how balloons work. They're either hot air balloons, which are less dense than the stuff around because they're hotter, or it's a different gas. I guess in this case it's a different gas. And I don't know how high they get up. Maybe, oh yeah, it says 128,000 feet, and then it jumps out. So I guess we know from what we did at 10,000 meters, 30,000 feet, that the air is pretty thin by the time you get there. And so I guess that's probably why he's wearing essentially a spacesuit, and I'm sure with oxygen. And he's free falling, and then I guess ultimately going to pull out a parachute and stop. So yeah. So he looks like he's been jumping out of planes about as much as I am. So where's it gone? So yeah, so I think interesting thing to watch. And so the other fluid mechanics part of that is, of course, what speed is he doing when he comes down? I think it clocks him. I don't know whether it says it on, I guess there are no closed captions. It says something like a 7 going supersonic. So the speed of sound is something like 600 plus miles an hour. And maybe he was doing 700 miles an hour, I seem to remember from a replay of this. But that would be at high altitude. And I think terminal velocity of people, of objects falling through the air, is something like 200 miles an hour. And so we will talk about why that would be today. It's pretty straightforward. It's just a balance of forces, gravity pulling you down and drag acting against you. Do they have? Yeah, okay. It must be miles an hour. So that is supersonic. I don't know if he had a sonic boom that accompanied him. I suppose he would do. Whoa, give me some more beer. So anyway, so that's Felix Baumgartner. I don't know. Well, 128,000 feet is, yeah, you're in space. Actually, there is some kind of debate about where space begins, right? Because the Virgin Galactic, or whatever it is, they want to call everyone astronauts. And there's some official definition of where space begins. And it may be different from NASA than it is from other bodies. It may be higher, maybe actually higher than Virgin Galactic go, which of course is dropped off a jet and then flies up to the stratosphere. No, this isn't. Well, Reading, that's actually on my way to Heathrow Airport, I suppose. Kind of interesting little jet engines on your arms, like Edward Scissorhands, or what is it? Edward 40 Hands? Yeah? Yeah, my son told me about that. I couldn't imagine doing that. Never done it, but sounds kind of interesting. And what is it supposed to be? Colt 45? Yeah. Fine. Well, yeah, you think I'm so square, but man, I know this stuff. So the other thing related to what we're doing now is, of course, settling. This is a high school video. I guess HHS must be not Health and Human Services. I presume it's something high school. And the other side of, I guess it's called, don't want the music. And so one way of sorting different size fractions or different density particles is to dump them into water, and then they'll settle out at different rates. The settling is controlled by the density of the particle and the size of the particle, both. And so you know that when you prospect for gold in the Sacramento River in California, you swirl it around in a pan to be able to separate it out. And of course it gets separated by the centripetal force and settling. It's done on the fact that gold is actually a pretty heavy particle compared to the other things around it. And so the same, if you just dump them into a column, you can measure the size fractions of different soils by looking at the rate at which those size fractions sediment, which you can actually measure as they do it here. And of course, the reality is that when you look at rocks or soils, they have some kind of structure in them, with the larger particles settling out first, and the finer particles taking much longer to settle out. And so you get these fining upwards sequences where the big particles settle out first, and when you get a landslide or in an estuary, the fine particles get carried further away from shore into the abyssal depths and get deposited with some kind of structure attached to them. And so that is something that happens in nature and something that is put to good use in trying to separate gravity separations of different particles. And I guess you can see the same thing for fluids inside fluids. There's no reason, I think, the things that we're talking about, you couldn't actually look at a bubble. Bubbles rising in beer after Thirsty Thursday. You know, a bubble is just a sphere that has water squeezing around it. You could imagine it as some kind of drag around it. Or if you put ink into water which has different density, ink presumably would be denser, or whatever this fluid is in this case, which is blue, is denser than the carrier fluid and causes these kind of weird and wonderful patterns. But the main portion is that it's, I guess that was a model, but the main point is that it's sinking as a result of negative buoyancy. Right? And the negative buoyancy, we could calculate the rate at which it goes down, I guess model on the left and actuality on the right. For congruence is to look at how you'd be able to represent that. And so that's kind of the culmination of what we may do today. I guess that's the point. So, and you see it once again. So that's kind of what we'll cover today. So, if you go back to what we talked about last time, a lot of stuff we didn't talk about, but I guess the main point we're trying to make is that if you want to calculate, I have to go back another one. I guess this is a short one. If you want to calculate the drag that is applied on something, it's quite easy for us to do that. And we can think of it merely as a force. And that force is kind of epitomized by the diagram which is in here, which is you can divide the drag or the lift into two components, one which is due to pressure and one which is due to viscosity or viscous drag in this particular case. And the components are additive in that if we want to evaluate what they are, we can look at the magnitude of pressure acting on the surface and shear stress acting on the surface. We merely had to resolve it in the right direction, which for drag is in the direction of flow, and for lift is perpendicular to that direction. And if we can do that, we can calculate, as we did last time with this numerical model, what the magnitudes of this coefficient of drag or coefficient of lift might be, just by evaluating what the drag force is, and then codifying it just by dividing it through by these terms, which allow us to represent it as an Euler number, where a force divided by an area is a pressure, and an Euler number would be a pressure divided by density, velocity squared, and the half creeps in just from Bernoulli as a functional relationship that gets left in the definition of drag coefficient and lift coefficient. And if we look at the magnitudes of these drag coefficients or lift coefficients, they look just like the magnitudes of friction factors that we have from before, in that they transit from being laminar to turbulent as we increase the velocities of flow, and their dependencies change from being related to viscosity in the laminar regime and due to density only in the turbulent regime. So that's kind of what where we have got to. And so what we might do today is kind of use that knowledge to try and solve those simple problems. We can solve for Felix Baumgartner jumping out of his Red Bull chariot as it goes up. And we can also do creeping settling for the other regime. So maybe it's worthwhile just repeating that. So What we're looking at is a figure that looks like this. Can't repeat yourself too often, maybe it's boring. But if we look at magnitudes of drag coefficient and magnitudes of lift coefficient, then they settle into this general regime here. This is Reynolds number, which is equal to a velocity, a length, a density, and a viscosity by definition. And this is a drag coefficient, which is really an Euler number. That's a non-dimensional number, which is this. I guess I don't need to write it because you have it right here. This length is some characteristic length, which would be also factored into the characteristic area. And we said last time, our parting shot was that if you're looking at lift on a wing, maybe the area would be the planiform area of the wing that is being sucked up. If you're looking at drag against the leading edge of the wing, maybe the area is the frontal area of the wing as you're looking at it. And of course, the length dimension would be either the width of the airfoil or the height of the airfoil, depending on the system, primarily because that's an important feature which links the physical behavior of the drag coefficient to that physical system. So it might change depending on what characteristic you're looking at as drag or lift and the characteristic of your system. And not surprisingly, we have this demarcation occurring. It typically is about, for pipe flow, it was 2000, remember, the transition to Reynolds number. So typically order 1000 or 2000. It's laminar on this side, and it's turbulent on this side. And laminar. And I guess the little figures that would show that would look like this. If we're scaling it along here, and you know what I'm going to draw. Why did it do that? This would be this, creeping flow. This would be initially separating flow. Remember, we had an airfoil that had this recirculation at the back of it. Doesn't really matter what it looks like. And we have this, which is much more fully developed flow with these vortices on the trailing edge that just represent the fact that they are occurring at different magnitudes of Reynolds numbers. And based on that, we can define the behavior. And I guess the other thing that we could also do is that we could write that the drag force or the lift force in squiggly characters would be equal to the integral tau dA plus the integral P dA. And I specifically split them either side of this because they are these different influences. This is viscosity dominated. This has the biggest effect. This is where density is dominating because of the pressure, killing the pressure against your chest or against the truck at SFO. And these are integral, squiggly integral signs, and therefore we can define that behavior. We'll see in a moment if we skip down here. I'm going to come back up. If you look at these relationships for real materials, either for a sphere, which is this case here, or for a cylinder going into the page, then for a sphere, this characteristic here for the drag coefficient is equal to a coefficient divided by Reynolds number. And this coefficient is actually 24, as it turns out. It was 96, if you remember, for pipe flow. And so, again, as we stay on this side, the coefficient of drag is proportional to 1 over Reynolds number. And the coefficient of drag or the coefficient of lift is not proportional to Reynolds number here, right? Because it's dead flat, essentially dead flat. And so just as in pipe flow, the way that we solve these equations for these two different systems, this system would be the grains at Hilbert High School settling in the water column, perhaps laminar flow. Again, you attach yourself to the grain and think of the water moving past you. And for Felix Baumgartner, dropping through space, again, attaching yourself to him and watching the fluid go past them. So how we deal with these is going to be different in each of these circumstances. And so that is mentioned merely because it's really quite similar to the Moody charts which we were developing before. The reason that we have this low plateau for both of these systems is that we develop a boundary layer, I guess it's shown here, and that instead of having this distribution of velocities around the, so if this is velocity, the distribution of velocity would be something like this. Back to the far field velocity once you get a long way away from it, but to zero velocity at the wall because it's a sticky boundary condition, it attaches to it. And if you look at the velocity profile as you went away from this, then you'd find out that it's going to get crowded, but it would look like essentially a boundary layer and then this magnitude here. So again, it goes back to the background velocity a long way away, but it transits to that very quickly with this very thin boundary layer. This boundary layer eats up some energy, dissipates energy as vortices and heat and sound, I suppose, mainly a small amount of heat, but is much more efficient than this, which burns up a lot of energy because of Newton's law of viscosity. This would be x. Let's call it y, actually, because x more commonly is horizontal. So how the velocity in the x direction changes with y. If there's a large gradient over a large area, then it eats up a lot of energy by changing this. Here, there's a very sharp gradient, a large gradient, but over an infinitesimally thin area, so it's still a finite magnitude. Even though this might be almost an infinite gradient, then it eats up less energy in terms of viscous dissipation. So that's the reason for that. And so just like in pipe flow, that controls how we solve those problems. And is the reason why, if your group is doing why is a golf ball dimpled, is the reason why a golf ball is dimpled. So let's solve some problems. So let's do a sphere falling through the air or through water. We have a force balance. The mass of that sphere, or the weight, is equal to mass times gravity. The forces acting upwards are going to be the buoyant force, which would be equal to the volume of the sphere multiplied by the density of the fluid multiplied by g. And we also have a drag force which is applied on it, which would be, I guess, circumferential to the sphere. And that would be just our squirrely d, if I can do a squirrely d. So if we sum forces, no surprise. If we sum in the down direction, sum of forces equals ma. Acceleration is 0, so this is equal to 0. So you can look at the weight minus the buoyant force is equal to the drag. And we can get the magnitude of the drag merely by looking at our definition of this. So we can rearrange this in terms of drag coefficient. And I guess for all our problems, CD is equal to squiggly d divided by a half rho fluid v squared area. And we can rewrite that as the drag force being equal to coefficient of drag multiplied by a half rho v squared times A. And so this is where the two regimes start to differ, right? This is generic so far. So the two regimes differ in that the drag coefficient that we'll use is going to be different between each of these regimes. Here the drag coefficient is going to be constant. And here the drag coefficient is equal to constant times 1 over Reynolds number. And so let's do the laminar settling first. We know, we've already said that that gradient is this. So we can take that and define our behavior. So we can write this as the weight minus the buoyant force. If it's, the buoyant force is probably going to be small, but let's not throw it away yet. This is going to equal 24 over Reynolds number times half rho v squared A, which if we put in Reynolds number, it's going to be, Reynolds number is, you're going to have to keep me honest in this, a velocity. It's going to have a characteristic length. That characteristic length is most likely the diameter, just by definition. Perhaps I'll call it lowercase d, just to avoid confusion. Vd rho over mu. So 24, this is our Reynolds number, this is a half, this is rho v squared pi, what's the volume of the sphere? 4/3 pi d cubed, or is it 4? 4/3? And then we just have to start messing around. Densities should cancel out. We should be left with a viscosity. Diameter, at least, should cancel out. A velocity should cancel out. And so we're left with some known, which are these parameters which are absolutely known, is equal to 12. Mu v pi 4 over 3. Do I have one extra pi in there? I do, right? D squared, which is equal to 48 over 3, right? Times v. And so we can rearrange that just as velocity is equal to W minus FB. So you're already ahead of me on this, I'm sure. 48 over 3 times pi. Pi is 3, so actually these essentially cancel out. Mu d squared equals v.
It should be r squared.
What should be r?
For a sphere. Radius squared.
Oh yeah, so it's over r squared, yeah. So 4 over 3 pi d cubed equals D is D is R over 2, right? R squared, right? That's what you're saying, isn't it? R squared equals D over 2 all squared. So cubed. So it's 8, right? There's an extra 8 in there somewhere. One over 8. Thank you. And that's it. So do the units match up? So we have newtons divided by newtons per meter squared times seconds times meters squared. Shouldn't be 1 over, oh yeah, should. Newtons cancel out. Do we have an extra? Is this just Pascal seconds, meters squared, newtons? Where did that extra m squared come from? Ah, yes. This, what happened? Yes, so this is 4 pi a squared, which is equal to 4 pi d squared upon 4. So yeah, d squared. So you lose this thing. Is this a 4 instead of an 8? And then if this is, so it's newtons per meter squared, seconds, meters, which is meters per second. Yeah, fine. So that's a good one. So how is it going to go to the next one now? So anyway, so if you know the weight is going to be the volume multiplied by the density times unit weight. This is going to be the buoyant force, which is the unit weight of the fluid multiplied by the volume. So you know these parameters. You know the viscosity. I guess if it was water, it would be 10 to the minus 3 Pascal seconds, roughly. And whatever the diameter would be. And then, of course, I guess you'd have to check that the Reynolds number is less than 10 to the 3, right? To make sure that you really are in this regime. So that would be the requirement for this. For jumping out of a plane, you almost certainly are going to be turbulent. You don't need to take that on trust, but you can do the calculation after the fact. We can go through this again, and what would be the relationships. So again, it would be W FB W. It would be forces in drag acting against it. And the same expression as we had before. That the drag is equal to this. So the basic expression is that W minus FB equals D, squiggly D equals coefficient of drag times a half rho V squared area squared, should remember. No longer can we get rid of using Reynolds number in this, so it's maybe used a bit easier because now the drag coefficient is a constant. We need to know what that constant is. For a sphere, it would be something like this. So I guess if you project that back here, it's something like 0.4. So this number would be 0.4. And you can see that because Reynolds number doesn't get entrained in this, no longer is viscosity going to be part of the solution. viscosity ends up in the solution because viscosity doesn't enter it anyway. But you're going to have to end up with a velocity which you'll square root to be able to solve it. And so I guess if we rearrange this, I'm not sure whether I want to go through the manipulation. This would be equal to weight minus buoyant force divided by 0.4 times a half times the density of the fluid times the cross-sectional area. Shouldn't be squared, right? It should just be area. Length squared. And that's equal to velocity squared. And so square root both sides. And you can also calculate what the units should be. So it should be newtons divided by kilograms per meter cubed times meter squared equals Newton meters per kilogram. So a Newton is the force required to give a kilogram an acceleration due to Newton. So Newton is the force required to give, so Newton is a kilogram meter per second squared, kilogram meter. Kilograms cancel out, and you end up with meters squared, seconds squared, square root. I might have actually done an example right for once. Just meter, shouldn't. Oh, that's not a nice laugh. There it is. That's it. And so different dependencies. That's about as simple. It's about as simple and as complicated as I can make it at the same time. But then, I guess also, then you need to check that the Reynolds number is greater than 10 to the 3. I guess that's my. And if that's the case, then you have a solution. Just need to check. And so that's about as simple as I can make it. So there's all kinds of coefficients that act to define exactly what this behavior would be in the laminar regime. I think I've gone past them here. This is the notes that are exactly, this comes out of the textbook. These are all for laminar flow, flow past a disk, 20.4 divided by Reynolds number. The characteristic dimension would be D, and the A would be the area of these things, the frontal area. Also for a flow parallel to a disk, I guess infinitesimally thin. The sphere we've just did, and the Haas sphere is only slightly different from this. So these obviously are all for laminar flow, not for turbulent flow. And if you want to use turbulent flow, then you have to use the ones after that. So what else do we talk about today? The reasons for this behavior are because of this. I don't know the reason for this little drop here, but certainly the drag coefficients are much lower when you have this boundary layer develop, which allows the object to scoot through the air much more effectively. So we just did this. So if you feel you're not sure what we just did, this is basically the same solution. This is for laminar flow, and you see it's a function of viscosity that you have to solve for. And if it's turbulent flow, this is just the idea, an example looking at hailstones being lofted up into a thundercloud. The way that hailstones grow is that they're lofted up by the updrafts, and they get water plated onto them and frozen until they're too heavy to be carried up, lofted up into the top of the cloud, and then they fall as hailstones and hopefully don't hit you on the head. But same idea is that in one case the solution will involve creeping flow, and we solve directly, and the magnitude will include viscosity in the solution, and the other one for turbulent flow will be a square root term on this, and it won't include viscosity at all, just as the rationale that we talked about in how these features wash out. So that's kind of it. The other things that we could talk about, well, we could talk about all kinds of behaviors. This is the golf ball idea, and so the reason for having dimples on a golf ball is that if you put a golf ball in a wind tunnel that is smooth, then the drag coefficient that you get for it conforms to this, where this is the Reynolds number for the flow with the diameter of the golf ball. I guess this is equal to velocity, diameter, density over viscosity. So kinematic viscosity is just equal to the dynamic viscosity divided by density, just by definition. That's what this term is here. And by putting dimples on it, what it does is it makes the boundary layer develop at a much lower velocity. And so for a golf ball with dimples, then the boundary layer, that is the transition from this flow regime to this flow regime, which kind of intuitively you'd think would be less efficient because you've got this turbulent wake that you'd think would be a disruptor on the flow. The reality is that having only a very thin boundary layer makes it quite efficient in going through the air. So that's why you get this drop from creeping flow at slow velocities here for fully developed thin boundary layer flow here. So putting dimples on a golf ball, all it does is it makes that transition happen at a much lower velocity. And so for a golf ball, they give the roughness. This is the same as the roughness that we talked about for pipes. Epsilon is the amplitude of the roughness. So this is essentially 10 to the minus 2. So a golf ball is what, 25 millimeters? So this would be 2 millimeters, 0.25 millimeters if this is 10 to the minus 2. So this is 0.2 of a millimeter in terms of the depth of the craters on a golf ball. Sounds about right, I would think, right? It could be a millimeter. I don't think it's as big as a millimeter, but it's certainly of that order of magnitude. And so that's the reason why you have that. What else? Ships. Composite bodies. So from a practical standpoint, if you want to design a water tower in State College that doesn't get blown over, you might want to know what the strength of the foundation would be to be able to do that. And you can look at the moments that would be applied to do that. The drag acts horizontally. So if you're looking at the net weight that's applied on the tower, it won't be very much. I mean, it would be weight. The effect of the flow around it, I guess you could imagine that flow over the top could give you some lift because it's not symmetric below, but probably not very much. But the main force would be to drag on each of these cylinders. And so if you wanted to solve that problem, then it would be calculating what the drag on the cylinder would be multiplied by the height of the cylinder, and the drag on the sphere multiplied by the height of the sphere. And so that would be equal to the net moment acting on the bottom, and it'd be very easy to write this as the sum of moments have to be equal to the drag for the sphere, which you could calculate from all the things we already did, multiplied by its lever arm, which would be HS in this particular case, plus the drag force on the cylinder, multiplied by the midpoint on the cylinder. So you can certainly calculate this from what we've looked at from these expressions here. I don't know exactly how this, you could do it from this. Of course, this smooth cylinder has to be defined. I guess the force that you'd calculate would be for a smooth cylinder per unit length into the page, right? Because a cylinder has an extra dimension which isn't as compact as a sphere. So you'd have to work out exactly what that is. I don't know what that is offhand, but you'd have to be mindful of that in calculating that composite drag. And as a result of those, you could calculate what the moment you'd have to design against. And so you could individually use the solutions for a sphere and a cylinder to be able to calculate that. And so these are just the equations for the sphere and the cylinder that we just did. And you have enough there to be able to calculate what's going on. Yeah, okay. And here, since they're using magnitudes of those drag coefficients, clearly it's turbulent in air for the wind. And you would check that with the magnitude of the Reynolds number. You can do it, and these tables exist in the book for, again, composite drag for looking at the drag forces applied on a car by adding the drag force from the front of the car to plus the windshield, plus the roof, plus the back of the car, etc. So sum all those components up to calculate the composite drag, and then use the CD is equal to the drag force you have to apply relative to a half density of the fluid times velocity squared times some frontal area. And of course the utility of doing this, I suppose, is that you could also calculate the amount of work you have to apply to push the car along, being equal to the drag force times the velocity, right? This is equal to a force times meters per second, which is equal to Newton meters per second, which is a joule per second, which is equal to a watt, right? So if you know what the drag magnitude is, and you know the velocity, which will also be a function of velocity, by the way, right, because of this. If you know what the magnitude of the drag force would be, and you know how fast your car is going to go at that drag force, then you immediately know how much energy is going to be eaten up in driving it against the air. Evolution of drag from Al Capone, I guess, to now, I don't know. Are we something else now? One of those Hondas with the cowlings over the wheels that used to be around. Don't see them anymore. And again, drag coefficients that are defined for all kinds of different structures, including things like, there's a flag in here somewhere, isn't there? No, don't see a flag. Oh yeah, here's a flag. Parachutes, a fluttering flag based on different characteristics. You have to decide whether the flow would be laminar or turbulent, but I presume that since these are constants related to the areas, then not functions of Reynolds number, that these are all for the turbulent regime, where you're not worrying about viscosity. So anyway, all kinds of ways to do that. And what else? I only have one other thing. I think the other interesting thing is someone must be doing, why does a baseball curve? And I guess my parting shot may well be this, which is not a baseball, but it's a ping pong ball. And so you know that, a table tennis ball, and you know that if you playing table tennis, the only shot I have is the chop. Can't get topspin on it. That never works out well for me. Topspin gets it over the net and then gets it to dive on the other side. A chop puts backspin on it, puts it up in the air, and it kind of stalls and falls backwards and perhaps jumps back into the net. And so the mechanism by which that occurs is, if you imagine putting spin on a sphere, you can imagine that the flow regime around that is a composite of two things. One would be that you're pushing the table tennis ball through the air, doesn't work for us. So imagine holding the table tennis ball static and having the air flow past it. And so that would be if you're hitting the ball in this direction, then it sees the air flying past it. If it happens to be a creeping flow, laminar, then it would look something like this. Stagnation point on the front, goes around, disconnects at the back, and provides this flow. If the ball, in addition, is spinning, so imagine a ball that's not moving, but is just spinning in space. What that ball will do is it will attach the air to it at this point, and it will carry it with it as it spins around. So I suppose if you drew the velocity of the air around this ball and looked at it at this particular location, then it would kind of look like, like this, right? It would be going, if you're attached to the ball and you're spinning around at that speed, then the velocity at that edge would be 0 relative to you because it's attached to you and it's spinning. But if you look further away, then in the distance, that air is static and you're moving around. So it looks as if the air is going fast here and going at 0 velocity here. So I've kind of done it the opposite. Here, I suppose the other way you could think about it is it's going really quickly here, and in the distance, it's going at 0 velocity. Oops, didn't want to do that. Right? So the real velocity here is 0. As you get to the ball, because the ball's spinning, it's going around. And so if you use what's called superposition, adding those two flow regimes, you get a flow regime that looks like this. That the stagnation point, instead of being here and the separation point being here, is changed from being this location here and this location here, just on account of this flow velocity. And so what you can think about that as being equal to an airfoil. Right? What we said the way that an airfoil works is that the flow comes in here, goes along the top, and it wants to join up with its buddy at the bottom, and the flow that goes on the bottom just carries on here. So in going from here to here, or from here the longer distance in the same time, because it doesn't want to cavitate and make a vacuum at this point, it has to be continuous. So the velocity top has to be, higher than the velocity at the base, which is lower. And from Bernoulli, we know that if the velocity increases, it does it at the expense of pressure, and so there's it acts as a wing, and so it gets lifted. And so when you put backspin on something, it just lifts it in the air. And it seems to kind of hang in the air, and just by that. If you put topspin on that, I suppose it would come in, so the stagnation point was here, and went around here, and then came off here, and then the lift would be the opposite. So it'd be like flying a plane upside down, which I guess you never want to be in, and it would pull it down. And so that's why when you put topspin on top of the table tennis ball, it dives. And I guess it's the same, well, it is the same, right? When you spin a baseball as you throw it, you get the same effects. And you can come up with the equations that define that behavior. And that's probably it. Yeah, that's it. That's it. A torrent of questions? No. So that's about as simply as I can state exactly what you have to do in these systems. It's all a matter, and I think it's good to have a look at the big picture. And the big picture isn't very different from pipe flow to external flows, internal flows versus external flows. And it really revolves around this idea that we can define some friction factor or a coefficient of drag. The dependencies on that changes as a function of the flow regime. At very low flow velocities, the component that's slowing down the flow in the pipe, or providing drag to the structure that's pushed through the air, is a function of the viscosity because it's creeping flow. And as the regime changes so that the Reynolds number increases as you increase the velocity, the geometry of the flow changes as well. And I guess I didn't talk about, perhaps it was in this, that's why I didn't talk about it. We didn't talk about von Karman vortex streets. And I mentioned it, but I don't think we ever looked at the expression for it. And I'm not sure. This looks like it here. And so maybe the parting shot, since you don't have any questions, which is unusual because you're usually very verbose, is to do this. And so, this is your, I presume, do you see this? I always say this, but I've never been to high school in the US, and I can't remember whether our kids saw this. Do you see this in your high school physics classes? No? Yes? No? Fine. Tacoma Narrows Bridge, well, you might not if you're in Saudi Arabia, but this is Seattle, this is Puget Sound. So this is just before people knew better that it's not a very fast wind. It was just a constant wind that didn't change. And the idea is that it sets up an oscillation on the bridge by taking the bridge deck, and it sheds a vortex sequentially from the top, and then the bottom, and then the top, and then the bottom, at a very specific relationship between the airflow across the bridge and the geometry of the bridge. And so-called galloping Gertie, I guess it was in the 1950s. We already lamented the fact that the guy's dog was left in the car and unfortunately perished as the bridge pulled itself apart. So it's if the frequency of the bridge, its natural vibrational frequency, is the same as the frequency that the vortex shedding wants to excite it at, then it ends up in resonance and the amplitude of it builds. So I'm not sure what the frequency is. It was a cycle every 2 seconds, right? So it's half a hertz or something like that. So that's the frequency that bridge is vibrating with. And so the expression, and I haven't checked whether it works out to be this or not, is the so-called von Karman. Von Karman was a famous German, probably got out of Germany after the war, worked at Caltech, just like Werner von Braun for the space program. And this is the idea, is that if you have a structure with an air flowing past it, then it sheds off a vortex from the top, and then the bottom, and then the top. And the characteristics of this, the frequency at which this occurs in hertz would be equal to the velocity of the flow divided by the diameter of the structure. This, I guess, would be the box girder characteristic. So I imagine that's about 10 meters or so, right? Probably a few meters high and maybe 10 meters wide, I'm not sure. And the Reynolds number at which it flows. And so the Reynolds number would also have a length in it, I guess as you see up here, a velocity, the airflow velocity, the density of air, 1 kilogram per meter cubed. What's the viscosity of air? Something like that. The diameter, order of 10 meters. I think the velocity was something like 30 miles an hour. It wasn't a big velocity, but it was a constant velocity. And you could check that if you wanted to, exactly what the Reynolds number would be defined, and you could calculate what the frequency should be for that particular characteristics. So if you design a bridge, you design it either that you can control all these things, but you can control the natural vibrational frequency of the bridge. And so the most recent example of that was the Waterloo Footbridge. In London. Jubilee bridges. They got a video of that. Doesn't come up with videos. Doesn't come up with videos? Images? No. Anyway, they built a footbridge across the Thames in London. They designed it badly, even now, so that when people were walking across it, it had this natural vibration that was very disconcerting people. So what do? Sometimes you see it on power lines, you see weights hanging off utility lines. They're just to change the characteristic frequency of that line so it doesn't wreck itself in a particular wind blowing across it that gives it resonance. And bridges are the same things. And so you just design the bridge so that the actual elastic frequency, just like twanging a guitar string, is different from the natural vibration frequency that's set up by the air flowing across it. So that's it. Was it that bad? So, that's all I got for you. So next week is happy hunting. Remember, 2 of them, Monday and Friday, are in Pollock, and the middle one is in the comfort of wherever you want to do it. And you have the stuff. This is old hat for you now, right? You know how to do these things. So I'm around today if you want to ask any questions, but you don't. But I'll be around. Good luck. So happy hunting. I think people have the hang of these now, and everything's working out well.